class 5 in ring theory. So far we have finished group theory, and in ring theory we have started defining ring theory, and then we have solved many problems based on they will give one set, we have to verify that set is a ring or not, and then we have moved on to subrings, right? So subrings, and then we have seen isomorphisms of rings and then subfield. So now we are going to move on to ideals, right? So we are going to discuss ideals today, right? So ideals. Right, so ideals, it is what similar to normal subgroups, right? So in group theory, we have seen normal subgroups. After define normal subgroups, we will define quotient groups. So similar way, first we are going to define what's meant by ideals, and then we are going to see some problems and theorems based on ideals, and then we will define quotient ring with the help of ideal, right? So you know, like for example, normal subgroup, right? So normal subgroups. So if G is a group, H is said to be normal if G and G inverse belongs to H, right? So that is the definition for normal subgroups. So just recall all the previous videos. So now we will define what is meant by ideals now, and this paves way for quotient ring. So first we will define ideal. So when I say ideal, first we have to define left ideal and then right ideal, right? So first we will define left ideal and then we will define right ideal. So left ideal, right? So left ideal, a non-empty subset S of a ring R is said to be left ideal. So this S is a non-empty subset of R, non-empty subset of a ring R, right? So we have a ring R, we are taking a subset. Remember, we are taking a subset, not a subring, right? A non-empty subset S of a ring R is said to be left ideal. A non-empty subset S of a ring R, this will be a left ideal. This will be a left ideal if it satisfies two conditions. The first one is this S has to be a subgroup, right? So S is a subgroup of R with respect to addition. With respect to addition, because in ring we will have two operations, addition and multiplication. So this set first has to be a subgroup of R. R is a ring with respect to addition. That is, when we say a subgroup will be this is subgroup, right? This subgroup. So for subgroup, it is enough to prove that AB inverse belongs to H, right? So for that, what you have to do is you just take two elements in S and you just verify AB inverse belongs to S. AB inverse belongs to S. Then this will be a subgroup. Now first this subset has to be a subgroup, and now this will be a left ideal. You just take two elements, R into S will be in S for every R belongs to R and for every S belongs to S, right? That is, it should be closed. So we have a ring R, so we have a non-empty subset S, and this set will be a left ideal, First, this has to be a subgroup, so that means AB inverse should be in S for A comma B belongs to S. For A comma B belongs to S, for A comma B belongs to S, for A comma B belongs to S, AB inverse belongs to S means it will be a subgroup. Now, for you just take some element R in R, S in S, right? So R is in ring R, S is in S. Now RS, remember the way you multiplying is important, right? RS, R into S. So R into S we should be in S for every R and every S in S. So if that satisfies, if these two conditions satisfied, then this S will be a then we are going to call this non-empty subset of R to be a left ideal, right? Left ideal. So this non-empty subset of ring R is said to be left ideal. So first this S has to be a subgroup, and R into S should be in S for every R in R and every S in S. Now we will define right ideal. RIGST, right ideal, right? So this is first definition, and this is second definition, right ideal. Similarly, S is a non-empty subset of R. S is a non-empty subset of R, of a ring R, right, of a ring R, then this non-empty subset will be a right ideal, will be a right ideal. So first the same condition, S is a subgroup, S is a subgroup with respect to addition, and second condition is here R into S belongs to S, here S into R should be in S, S into R should be in S, and remember R into S and S into R are different, right. Suppose if our group is a abelian group means then R into S and SR will be same. Suppose if our group is not abelian means, that is if it is not commutative means, then these two are different element, that is R into S and S into R are different element, right. So for example, if you take matrices, then if you take R and S to be two matrices, then R into S is RS and SR need not be same. So they need not be same, right. So here what we are doing is, so left means this R should be in left, and this right means this R should be in right, right. So left ideal, right ideal. So left means the bigger set should come first and then smaller set. Right ideal means smaller set should come first and bigger set should come second, right. So but the first two conditions are same. Here R into S, here S into R, right, is. So we have defined left ideal. So a ring R, a subset S, and this subset will be left ideal if this subset is a subgroup and this subset satisfies R into S belongs to S for every R and S belongs to S. And right ideal, S into R should be in S for every R belongs to R and for every S belongs to capital S. So we have defined left ideal, right ideal. Now we will define, whenever I say ideal, you have to think that of it is left ideal as well as right ideal, right. So a non-empty subset of a ring R is said to be an ideal if and only if it is both left ideal and as well as it is right ideal. So the third definition is ideal. So left ideal, right ideal. Now we will define ideal, right. So it is similar to the in analysis we will study bounded, right. So first for defining bounded, so first we will define what is meant by bounded above, and then we will define bounded below, and if a set is bounded above as well as bounded below, we will say it is bounded. So similarly, so we have defined left ideal, now we have defined right ideal. Now we are going to say call ideal, right, ideal. So again a non-empty subset, S of a ring R, is said to be ideal if and only if it is both left and right ideal, right. So it has to be left ideal and as well as it has to be right ideal. So if you want to write as a condition, so it has to be left ideal as well as right ideal, right. So we have here two condition, for left ideal two condition, for right ideal two condition, and one condition is common. So first this S is a subgroup, with respect to addition, and second is R into S should be in S for every R in R, S in S. Third condition is S into R should also be in S for every R in R, for every S in S. That is, it has to be left ideal as well as it is right ideal, right. So whenever you need to prove ideal, you need to verify these three things. First is, this is a condition for left ideal, right. Left ideal means left. So just imagine that bigger set should come first. So left, right, left, right, left. So here right ideal means, so in bigger set should contain right. So S into R should be in S. So far we have defined left ideal, we have defined right ideal. Now we have defined ideal, right. So when I say ideal, it has to be left ideal as well as it has to be right ideal. So for you can see that this is a subgroup with respect to addition, right? That is, you need to put that is subgroup with respect to addition. So it is enough to show for this. It is enough to show. We need to show AB inverse belongs to H, right? AB inverse belongs to H, and we know the inverse for A is minus A if the operation is addition. So it is enough to prove if you take two element in S and if A minus B belongs to S, then this is a subgroup with respect to addition, right? So you just take two element in S and you just prove that A minus B belongs to S, and also that every ideal of a ring R is also a subring of R, but every subring is not ideal, right? So every ideal will be a subring and every subring will not be an ideal. Suppose if the ring is commutative, then left ideal is same as right ideal, right? So suppose if you just take note, suppose if R is commutative, then AB is same as BA. So if R is commutative, then left ideal is same as right ideal, because RS and SR are both are same if the ring is commutative. So therefore when the ring is commutative ring, then left ideal is same as right ideal. Every ring R possesses two improper ideals, one R itself, another consisting of 0 only. So every ring R possesses two ideal, that is that is going to call as improper. This is note 1, and note 2 is every ring R. So just take notes. So every ring R possesses two improper ideal, that is the set consisting of 0 and the entire ring R. So we are going to call these two ideals as improper ideals, and obviously and RS and SR will be both in S, right? So every ring R, here R is same as S, right? Here S is 0. So R is a ring, then S is equal to 0. A set consisting of only single element will be always an ideal, and the entire ring will always be an ideal. So we are going to call these two as improper ideals, and we are going to name this as unit ideal, and we are going to name this as null ideal, right? So every ring always have two improper ideal, which is the entire ring and a set consisting of 0. So we are going to call this as null ideal and unit ideal. So any ideal other than this, that will be a proper ideal. Any ideal other than ring is a proper ideal. A ring having no proper ideal is called a simple ring, right? So just compare with suppose if a group has no proper normal subgroups, right? If a group has no proper normal subgroups, so we will go back to group theory. So if a group has no proper normal subgroup, that is only subgroups are the set consisting of ID and then the entire group, we are going to call it as improper normal subgroup. Suppose if there is no other subgroup which is normal, we are going to call E and the whole group as improper normal subgroup. Suppose if there is no other subgroup which is normal, then the only normal subgroups of G are the improper normal subgroup, which is E and G. Now we are going to call that group as simple group, right? So if a group has no proper normal subgroup, then the group is called simple group, right? So in group theory we will just recall. So simple group is not in the syllabus, so I'll just tell you the definition. If a group has no proper normal subgroup, then the group is called simple group. So similarly, if a ring has no proper ideal, right? So there normal subgroup will be replaced by ideal here. If a ring has no proper ideals, that is the only ideals are 0 and the entire ring, then the group is called, then the ring is called simple ring, right? Simple ring. So simple ring means no proper ideals, no proper ideals. That means the only ideals of a ring are the 0 and the entire ring itself. So if a ring has, so you just take the node 3. Node 3 is, node 1 is this, node 2 is this, and for node 3, if a ring has no proper ideal, then that ring is called simple ring. Now we will be moving on to algebra of ideals. So algebra of ideal means if I have two ideal, what can I say about union, what can I say about intersection, and what can I say about sum. So these are the algebra I am going to do. So intersection of any two left ideal of a ring R is again a left ideal. So we will start moving theorem. So theorem 1. The intersection of any two left ideal is again a left ideal. It's again a left ideal of the ring R, right? So we have two left ideal, then intersection of these two left ideal is again a left ideal. So we'll prove this. So left ideal means so here let us take two ideal to be I1 and I2. So let I1 and I2 be two ideals. That means these two are ideal. That means this I1 with respect to addition, this addition is a subgroup, and if you take two element in so RS belongs to here we have I1, right? So whenever you are taking a two element, let us take R into some small I1. So R into some I1, let us say this small I1. So RI1 belongs to I1, right? So here it is R. So this is I1. So instead of S, here we have I1, and this is I2. So this is I1 is a ideal. That's one assumption. So if you take you just take some element I1 here and you just take R, then R into I1 should be in I1. This is a definition for left ideal. And similarly I2 is also left ideal. So I2 with respect to plus is a subgroup, and if you just take some other element I2 here, then R into I2 also in I2, because these two are let I be two left ideal, right? So the intersection of any two left ideal is again left ideal. So I will look at these two left ideal. So what I need to prove? Intersection, that is I1 intersection I2 is a left ideal. That means I need to prove that I1 intersection I2 is a subgroup with respect to addition, and if you take an element in I1 intersection I2, then R into this element should be in I1 intersection I2, then it will be a ideal, right? Yes. So first we need to prove, that is to prove first I1 intersection I2 with respect to addition is a subgroup, right? Second is you just take some element, let us take some element S in I1 intersection I2. Let us take some element S in I1 intersection I2. Then you are taking some element S, then R into S. then R into S should be in I1 intersection I2. I1 intersection I2. So if I prove these two conditions, then I1 intersection I2 will be a left ideal, right? So we will move on to prove this. So first we need to prove I1 intersection I2 is a subgroup, right? So we already know, since I1 and I2 are ideals, that means I1 and I2 is also a subgroup, is also a subgroup with respect to addition, right? Because you can see the first condition is that it is a subgroup, and we already know intersection of two subgroup is again a subgroup. This we already discussed in group theory. So I1 is a subgroup, I2 is a subgroup. This implies intersection of two subgroup is again a subgroup. Intersection of two subgroup is a subgroup. So we have proved the first condition, that is I1 intersection I2 with respect to addition is a subgroup. Now I need to take an element S in I1 intersection I2, and I need to prove R into S also belongs to I1 intersection I2 for left ideal, right? So we will prove the second. So there is a proof for the first condition. Now for second condition, we are taking an element S in I1 intersection I2. So this implies S belongs to I1, S belongs to I2. So I am taking some element S in I1. This S belongs to I1. So since I1 is a left ideal, can I say RS belongs to I1? Right? Because I am taking S to be S is an element of I1, and since I1 is a left ideal, so whatever element you take from R into S will be in I1, because I1 and I2 is ideal. And again similarly, R into S belongs to I2 also, because I1 and I2 are ideals. Now we have RS belongs to I1 as well as RS belongs to I2. This means RS belongs to I1 intersection I2. So this means it is a left ideal. So we have proved that I1 intersection I2 is also a subgroup, and RS belongs to I1 intersection I2 for S belongs to I1 intersection I2. And now similarly, an arbitrary intersection of left ideal is again left ideal, right? So you can easily prove this also. So the arbitrary intersection of left ideal is again left ideal. So similarly, you just want to extend this. That's it. So we will extend this. The arbitrary intersection of left ideal is again left ideal. Actually, you can prove everything in your own, understand the definition of left ideal. And similarly, the intersection of two right ideal is also right ideal. So we have proved the intersection of two left ideal is a left ideal. Similarly, intersection of two right ideal is also right ideal. So instead here we will have I2 into R. Here we will have I1 into R, and here we will have S into R. Here we will have S into R. The only thing is you have to reverse I1 and R. That's it. So similarly, the intersection of two right ideal is also right ideal. Intersection of two left ideal is again a left ideal. Now the arbitrary intersection of left ideal is again a left ideal. So for theorem 2, you just have to replace I1R by RI1. That's it, right? Sorry, yes. So this theorem, the arbitrary intersection of left ideal is again a left ideal. It's again a left ideal. So let R be the ring. So actually I can put a similar proof, you just extend. So R be the ring. Right? Let S1, S2, S3, S4 and so on up to Sn be a subring of R. So what I need to prove? I need to prove intersection of Si I is equal to 1 to n is a subring. That means I need to prove two conditions. Intersection of I is equal to 1 to n with respect to addition is a subgroup. And second thing is, let us take some element s in intersection of I is equal to 1 to n si, and we have to left ideal, means that is you just prove rs also, you just take some element s. This implies rs also belongs to intersection of I is equal to 1 to n si. So you can prove the first very easily, because we need to prove intersection of si is a subgroup. We have s1 s2 up to sn are subrings. So this implies s1 s2 up to sn are subgroups, because subring means first it has to be subgroup with respect to addition. So therefore we know that intersection of subgroup is again a subgroup. So intersection of the arbitrary intersection of subgroup is again a subgroup. We already proved in group theory. Therefore intersection of si is a subgroup. Now the second condition is, so you just take some element s in intersection of I is equal to 1 to n si. This implies the small s belongs to s1, s belongs to s2, s belongs to s3, and so on up to s belongs to sn. So s belongs to s1 and s1, s2, sn are subrings. So can I say rs belongs to, sorry, s1, s2, s2 are subring, that is it is a left ideal, sorry, s1, s2 are be left ideal, sorry, because we need to prove arbitrary intersection of left ideal and left ideal. So let us take s1, s2, s3, s4 be left ideal. We need to prove that this is a left ideal again. So for left ideal, sorry, we need to put left ideal. I don't know why I have written subring. Right. So first we need to put the left ideal. So for that we need to prove that these two happens. So we have put first. Second one this. So already s1, s2 are left ideal. So therefore rs will be in s1, rs will be in s2, and so on up to rs will be in sn. So this rs belongs to s1, s2, and so on. This implies rs belongs to intersection of I is equal to 1 si. So we have proved intersection of si is subring, and then we have proved rs belongs to intersection of si for every r in r and every s in s. So we have proved that the arbitrary intersection of left ideal is again left ideal. Similarly, you can also prove the arbitrary intersection of right ideal is also a right ideal. Now we will move on to the third, that is first theorem. We have proved the intersection of two left ideal is again left ideal, and then we have proved intersection of two right ideals are right ideal. So you just have to replace ri1 by i1r, and we have proved the arbitrary intersection of left ideals again left ideal. Similarly, arbitrary intersection of right ideal is also right ideal. So I have proved arbitrary intersection of left ideal and intersection of two left ideals and left ideal. Similarly, you can right ideal by just replacing r into i1 by i1 into r, right? Yes. So now we will move on to theorem 3. So theorem 3 is sum of two left ideal. Sum of two left ideal, right? So we are going to define what is meant by sum of two left ideal. So let the left ideal generated by union of two left ideal now actually the ideal generated by the union of two ideal is called the sum of two left ideal. So the ideal left ideal, similarly you can also define right ideal also. The left ideal generated by union of union of I1 union I2 of two left ideal is the set I1 plus I2 consisting of elements of R obtained on adding an element of I1 to an element of I2. That is I1 plus I2 is nothing but set of all I1 plus I2, and this I1 belongs to capital I1 and this I2 belongs to capital I2. Right, set of all I1 plus I2. We can call this as sum of two left ideal. And you can clearly see the left ideal generated by union of I1 and I2 is this set, right? So we will get this set, and this set will be generated by the union of I1 and I2, right? Now actually you can it's a very easy proof. You can easily go through that this is also an ideal. For that you have to take two elements in I1 plus I2, and then you have to prove that it is a subgroup and it is a left ideal. So for that you need to prove R into S belongs to I1 plus I2. You just take some element S in I1 plus I2. You have to prove that, right? And also you can also prove easily that this set is generated by I1 union I2. For detailed proof you can refer page number 309 in Krishna series for the statistics book. So I1 plus I2 is set generated by I1 union I2. So we will see some examples for ideals. So far what we have did is, so first of all we have defined what's meant by left ideal, and then we have seen what's meant by right ideal, and then we will call a ring to be a left ideal. We will call a ring to be ideal if it is left ideal as well as it is right ideal. And then we have seen a theorem, the intersection of two left ideals again left ideal, and similarly the intersection of two right ideal is also right ideal, and the arbitrary intersection of left ideal is again left ideal, and arbitrary intersection of right ideal is again right ideal. And then we have proved what is meant by I1 plus I2. It is a set generated by I1 union I2, and I1 plus I2 is also a ideal. Now we will see some examples for ideals, right? So we will see some examples. The first example, the set n of 2 cross 2 matrices, the set n is equal to the set of all 2 cross 2 matrices, that is a subset of A, B, C. The set of all 2 cross 2 matrices is a left ideal but not right ideal. Is a left ideal but not right ideal. It's a left ideal but not right ideal, right? The set n of 2 cross 2 matrices of the form A0 B0, A and B are integers, right? A and B are integers is a left ideal but not right ideal. Here n is a subset of R consisting of those elements whose second column contains 0, right? So first we will prove that this is a left ideal but it is not, it is a right ideal. So first we will show that n is left ideal. So for proving n is left ideal, so first we need to prove that this n with respect to addition is a subgroup, right? So for addition it is a subgroup, we will prove. So for subgroup what you need to do, so as I already said, so for proving subgroup what I said, you just take two elements in n and you just verify whether A minus B belongs to n. It is sufficient to prove it is a subgroup. So just AB belongs to n means A minus B also belongs to n, then it is subgroup, right? So let us take two elements in n. So let us take A to B, or let us take two element AB in n. Now we will prove that A minus B also belongs to n. Let us take an element A to be A1 0 B1 0, and let us take B to be a2 0, b2 0. So here a1, a2, b1, b2 are all are integers, all are integers. Now what about a minus b? A minus b is nothing but a1 minus a2 0, b1 minus b2 0. This will also be in n because it is also of the form a0 b0, a1 minus b2, the sum of two integers again integer. Therefore a1 minus a2 is again integer, b1 minus b2 is again integer. So integer 0, integer 0. So this n will be this a minus b should be belongs to n. A minus b belongs to n. So this is a subgroup. Now we need to prove that the left ideal. That means Rs belongs to S, right? So Rs belongs to S. So here our S is n. Let us take Rn belongs to capital N for every R in R and for every N in N. So here we need to take an element R in capital R, that is a ring. So here the ring is set of all 2 crossed matrices and N is the subset of ring R consisting of the second columns 0. So here the entire ring is A, B, C, D and this A, B, C, D are integers. We are taking a subset N. We are taking a subset N. We are going to prove that this subset is a left ideal. So for that I have to prove that it is a subgroup. Now for left ideal Rn belongs to N, R belongs to R, N belongs to N. So let us take R to be A, B, C, D. Let us take this A, B, C, D and we have to take N in N. Let us take this to be equal to A1 0, B1 0. Now what about Rn? What about Rn? Rn. So Rn is A, B, C, D into A1 0, B1 0. So when you multiply this, we will have AA1 plus BB1. This will be 0. A into 0 plus B into 0. So here we will have CA1 plus DB1. This will be again 0 because C into C0 plus D into 0. So surely this also belongs to N because A1 plus BB1 is again integer because A1 B1 are integers and here also this ABCD are all integers. Then this R is M2 of Z. That are 2 crossed matrices over integers, integer entries, and this ABCD belongs to integer and this A1 B1 also belongs to integer. So therefore this entire element will be integer, this entire element will be integer. So it is of the form n, so therefore this element will be n. So therefore we have proved that it is a left ideal. Therefore we have proved that it is a left ideal. Now we need to prove that it is not a right ideal. We need to prove not a right ideal. So for right ideal it has to be subgroup and then it has to satisfy NR, right? NR should be in N. So NR. So for NR should be NR should be belong to N. This is the condition for right ideal. Clearly this is subgroup, right? It is subgroup because the first condition is same for left ideal as well as right ideal. So for what about N into R? So here N is A1 0, B1 0 into R is A, B, C, D. So when you multiply these two, so this is N into R. So this is A1A, and here we will have A1B, here we will have B1A, and here we will have B1B. So therefore this does not belong to N because N consists of all those matrices whose second column is 0, but it is not that here second column is 0, therefore this element does not belong to capital N. So therefore this is not a right ideal. It is a left ideal but it is not right ideal. So if you take a matrices, this matrices, that is 0 0 0 0 CD, then this will be a right ideal but it is not a left ideal, right? Now we will move on to the second example. So this example is a left ideal but it is not right ideal. So example 2. So we have proved this, right? We have proved. Now if M is a fixed integer, the set P of integers given by. So if M is a fixed integer, remember fixed integer, the set P of integers given by. So I'm going to call a set P as x into m, and this x is an integer. Is an ideal. Is an ideal. That means we need to prove that this is also left ideal and also right ideal. So for that, so first we will prove it is a so we have to prove left, not to prove ideal. So we need to prove three conditions. That is, it has to be left ideal as well as right ideal. So this set P with respect to addition has to be a subgroup, and you just take some element R. So R into P should be in capital P. So here the only thing is the sign is different, right? So in defining, we will define RS belongs to S. So instead of S, here we will have P. So RP belongs to P for left ideal, and PR also belongs to P. Here what this said, this m is a fixed integer. Suppose if you fix m is equal to 2, then we will have P to be equal to 2x, and this x belongs to integer. So if you vary x, so we will have 0 plus or minus 2 plus or minus 4 plus or minus 6 and so on. So similarly, if you fix m to be equal to 3, we will have some other p. So we're going to prove that this p is a left ideal as well as right ideal. Similarly, easily you can verify. So clearly it is a subgroup, right? So for subgroup, you just take two elements in P, you just verify whether A minus B belongs to P. So let us, here you can see let us take A to be equal to x1m, B to be equal to x2m. So what about A minus B? It is nothing but x1 minus x2 into m, and this x1, x2 are integers. Here x1, x2 are integers, x1 minus x2 is again integer. So integer into m is also in P. So therefore this again in P. So therefore it is a subgroup. So you need to take an element R. Here m is a fixed integer. Is an ideal of ring of integers. Here the R is integers, right? Here the R is integers. So you just take some element R in integer. Let us take R to be equal to, let us take R belongs to some integer, and here P belongs to, let P is equal to xm, right? So R belongs to any integer, P is of the form x into m. So what about R into P? So R is some integer, P is x into m. So R is some integer, R is an integer, R is an integer, x is again an integer, right? Because x belongs to x an integer, R into x again integer, and so therefore R into m is an integer, and integer into m will be in P. So therefore this belongs to P, right? And similarly P is again some integer, P into R. So P into R. So let us take P to be equal to xm and R. So R is some integer, because R belongs to the ring of integers. P, we are taking x, we are taking an element xm. So x is again integer. So therefore this also belongs to P. Therefore this is left ideal as well as it is right ideal. So therefore this set of all fixed integer is a ideal. So I can also, suppose if you haven't understand this proof, then let us verify for some fixed integer. Let us take m to be equal to 2. Then what this set contain? This set contains 0 plus or minus 2 plus or minus 4 plus or minus 6 plus or minus 8 and so on, right? Because this set is nothing but, if m is equal to 2, then p is nothing but 2x, and this x belongs to integer. So if x is equal to 0, we will have 1. So if x is equal to 1 and minus 1, we will have plus or minus 2. If x is equal to 2 and minus 2, we will have plus or minus 4. If for plus or minus 3, we will have plus or minus 6 and so on. So clearly this is subgroup, right? Just subgroup. So for subgroup, it is enough to say a minus b belongs to P, for a comma b belongs to P. If you take a to be equal to 4, b to be equal to 6, then what about a minus b? It is minus 2, and minus 2 is in P. And for left ideal, we will prove RP. Let us take R is from integer. Let us take R to be equal to 1, right? R to be equal to 1, and P is from this set. Let us take P to be equal to 2. What about RP? RP is 1 into 2, which is 2, and this belongs to P. And what about P into R? So P into R is, so P is 2, R is 1 again. This is also equal to 2, and this belongs to P. Therefore, RP also belongs to P and PR also belongs to P. So therefore, this set is a ideal. The set integers is a only subring but not an ideal of being operational numbers. Now example 3. The set integers, the set of integers, let us call that as I, is only a subring, is only a subring, is only a subring, but not an ideal of Q. That is, here we have R to be the ring is that are all rational numbers, and the subset S is integers, right? So this S is a subring, but it is not an ideal. So clearly this S is a subgroup, right? So first we need to put a subring. So for subring we need to check two conditions. So first we will prove S is a subring. So for subring, so if you take two element in S, A minus B should be in S and AB should be in S. Remember, it is subring, it is not subgroup. So if you take two element in S, if you take two element in integers, then difference of two integers again integer and product of two integers again integer. So therefore this will be a subring, right? So therefore set of all integers is only a subring but not an ideal. So we will prove that this S is not ideal. S is not ideal. So for that, so first we will check whether it is a subgroup. So clearly it is subgroup, right? S is a subgroup. S is a subgroup. Clearly it is subgroup of addition. So for subgroup it is enough to verify A minus B belongs to S. So it is subring means naturally it will be a subgroup. Now we need to check whether left ideal. We need to check whether it is left ideal. So for left ideal, R into S should be in it should be in S, and this R belongs to R, S belongs to S. So here what is our R? R is set of all rational numbers. Suppose if I take R to be equal to 1 by 2 and we will take S from the set S, that is all integers, let us take S to be equal to 3, then what about R into S? What about R into S? What about R into S? I think the code is not visible. Okay, so I will write here. So we need to prove that this set is a. So I will write here. So I think it is not visible. So we need to prove that this set is not ideal, but it is subring. So we have put the subring. So for ideal, we need to check whether it is left ideal, right ideal, and subgroup. So it is subgroup. So for left ideal, we should have RS should be belongs to S, and this R belongs to R, and this S belongs to capital S. So here R is R. So that means R is Q here. Let us take R to be equal to 1 by 2, and S is from integers. Let us take S to be equal to 3. Now what about RS? R is nothing but 1 by 2 into 3, which is 3 by 2, and this 3 by 2 does not belongs to S because S is that of all integers. That means it is not left ideal. It is not left ideal. Similarly, it is also not right ideal. It is not left ideal, not right ideal also, because S into R. So S into R is 3 into 1 by 2, and this also not belongs to. Remember, this R, S, this has to be true for every R and every S. Suppose you may ask me, if I take R to be equal to 1 by 2, if I take S to be equal to 2, then R into S will be 1 by 2 into 2, which is 1, and this 1 belongs to integer, but that is only true for one number, right? So it has to be true for every R and every S, right? So you should not argue that if I take R is equal to 1 by 2, S is equal to 2, then RS belongs to S. Therefore, it is left ideal. It has to be true for every R and every S, right? So if I take R to be equal to 1 by 2, if I take R to be S to be equal to 3, then for this R and S, it is not belongs to S. So this will be belongs to S for only one R and S, but it has to be true for every R and every S, and similarly it is also not right ideal also. So therefore the set Q of rational numbers, the set Q of the set of integers is subring of Q, but it is not an ideal of Q. So now we move on to example 4. The set Q of rational numbers, the only subring of ideal of real numbers. Yeah. Similarly, fourth, the set Q of rational numbers, the set Q of rational numbers is a subring of R, but not ideal of R. Right. So we have in the previous column we have proved a set integers is a subring of Q, but not ideal of Q. But here Q is a subring of R, so we are just extending, right? So first we have seen the relation between integers and rational. Now we are seeing the relation. First we have seen the relation between integer and Q, and this integer is subring of Q, but this integer is not an ideal of Q. And similarly, this Q is a subring of R, but this Q is not an ideal of R. Q is an ideal of R. So let us take R. R is a set of all real numbers, and this is a ring, and S is a subring of Q. So Q with respect to plus input R. So clearly S is a subring. So for subring, you just take two elements in S. You need to prove A minus B belongs to S, AB belongs to S. So if you take two elements in S, if you take two rational number, the difference of two rational numbers again rational number, the product of two rational numbers again rational number. So therefore this S is a subring of R, but it is not, S is not ideal. So S is not ideal. That means clearly it is subgroup, right? The first condition satisfies. S is a subgroup, right? So for subgroup, you just take two elements in S. You just prove A minus B belongs to S, A and B are in S. Now for it is not left ideal as well as it is not right ideal. So for left ideal, R into S should be in S, R into S should be in S, and this R belongs to ring R, and this S belongs to subring S. Now if I take R is, I can take any element R in the real number. So if I take R is equal to root 2, R is equal to root 2, let us take some other element, let us say it is equal to 2. I am taking an element Q in rational number, S in rational number. What about RS? So RS is root 2 into 2, and this element is not in S, because S contains only rational number. So 2 root 2 is an irrational number, therefore it is not belongs to S. Similarly, it is also not right ideal also, 2 root 2 is also not in S. Therefore set Q of rational numbers is subring of R, but it is not an ideal of R. So we will move on to some other examples. So example 5. So first example, we have proved set of all matrices of the form A0 B0 is left ideal, but it is not right ideal. In a second example, we have proved the fixed integers is left ideal as well as it is right ideal. And the third example, the set I of integers is a subring of Q, but it is not an ideal of Q. And for fourth example, we have seen the set Q. The set Q is a subring of R, but it is not an ideal of R. Now we will see example 5. So in an exam they will ask, give an example of an ideal which is left ideal but is not right ideal. You have to write, let us take the ring R to be the set of all 2 cross 2 matrices with the entries from the integers, that is R is equal to ABCD, 2 cross 2 matrices with ABCD belongs to integer. Let us take a subset to be S to be equal to A0, B0, that is the first column is AB, second column is 0. You just verify that it is a left ideal, but it is not right ideal, as I did in example 1. Suppose if they ask, give an example of an ideal which is right ideal but it is not left ideal. So you just take the subset of the form A00 CV, 00 CV, and this will be a right ideal but it is not a left ideal, right? Yes. So now we will give an example. Prove that the subset of example 5, prove that the subset of the form, the subset S of all matrices of 2 cross 2 matrices of the form A00B is neither with AB belongs to integer. Prove that S is neither right ideal, S is neither left ideal nor right ideal. This set is not left ideal and also it is not right ideal. It is also not right ideal. Right? So this is set of all diagonal matrices. Set of all 2 cross 2 diagonal matrices is neither left ideal nor right ideal. So first we will show that this is not left ideal. So S is not left ideal. So what is R here? So here the R is set of all 2 cross 2 matrices with ABCD belongs to integer. This is our R, and S is a subset of the form A00B and this AB belongs to integer. Now first we will prove that this S is not left ideal. This set is not left ideal, and then we will prove this S is not right ideal. So in the exam they will ask, give an example of an ideal which is neither left ideal nor right ideal. So you need to remember this example. So S is not right ideal. So we need to prove not left ideal. Let us take some element R in R, S in S, and if this element belongs to S, then this will be left ideal. You just take some element for every R and every S in S, and if this SR belongs to S, then this will be right ideal. Now let us take R to be equal to let us take some 2 cross 2 matrices, whatever you like. Let us take 2 1 3 4, right? So for proving not, it is enough to give one counter example, right? For proving not, it is enough to give one counter example. Let us take S to be let us take 2 0 0 3, because S is of the form diagonal matrices, R is the following. Now what about RS? So 2 1 3 4 into 2 0 0 3. So when you multiply this, you will have 2 2s are 4, 2 3s are 2 into 0, this will have 3, so 3 to 6, and this will be 12, and you can see this does not belong to S because this is not diagonal matrices, because this matrix is 4 3 6 12, which does not belong to S, because S contains only 2 cross 2 diagonal matrices. So this is not left ideal. Similarly, what about S into R? You just take same R and same S we defined here. So what about SR? So you just take the same R and same S. And what about RS? So RS is 2003 into 2134, and this will be 2 2s are 4, 2 1s are 2, and this will be 9, this will be 12, and again you can see this also does not belongs to S because this also is not a diagonal matrices. Therefore the subset A00P is neither a left ideal nor right ideal. Actually, there are some more examples. So prove that the intersection of two ideal is again ideal. So actually we have proved the intersection of two left ideals again left ideal, and also we have proved intersection of two right ideals also right ideal. Now we are going to prove the intersection of two ideals is again a ideal. So ideal means RS and SR should be in S, right? So we will prove this, and then show that S is an ideal of S plus T, where S is any ideal of ring R and T be any subring. And if U is a left ideal of ring R, then lambda U is a left ideal. Okay. Okay, first now I will prove this exercise 5. Now I will prove on to actually there are some small exercise like 2 or 3 line proof. If U is an ideal of a ring R with unity, then and 1 belongs to U, prove that U is equal to R. I think you can easily do this. The set of, if R is a ring and A belongs to R, the set of all x equal to 0 plus ideal of R, the set of all x is equal to 0. Okay, now we will move on one by one. So we have finished exercise 5. So exercise 6 is exercise 6 is, if U is an ideal of a ring R, if U is an ideal of ring R with unity, and if 1 belongs to U, then U has to be equal to R, right? So if U is an ideal of ring R with unity, and if 1 belongs to U, then U is equal to R. Again, see is in natural way, because so we have, this is R and this is U, and this U is an ideal, right? So this R, if U is an ideal, right? So since U is an ideal, that means it is left ideal as well as right ideal. So that means if you take an element, let us take some element R, for every R in R, remember, and this R is a ring with unity, that means it has unit element, that is a multiple entity. So let us take R belongs to R and U belongs to U, then RU will be in U, because if U is an ideal, then this will happen. And you can see, if I take here, and if 1 belongs to U, so since, and I am assuming that U is an ideal, and if also there is an element 1 in U, that is there is an element 1 in U, then U has to be equal to R, because since 1 belongs to U, let U is equal to 1, small u is equal to 1. Then what about RU belongs, because it's a left ideal means, so R into 1 belongs to U, right? So for every R in R, so that means if you vary every R into 1 is again R, so if you vary R, you will get the entire R, that means U is equal to R. I will repeat. So because it has a unit element, so because we have 1 here, so since it's an ideal, R into this will be in U, R into this will be in U, and if I take U to be equal to 1, because 1 belongs to U, what about R into 1? It will be U again, but R into 1, you will get the entire R. So therefore R has to be equal to U. Then this U is not a small set, both are same, because I can take U to be equal to 1 and RU will be the entire R, right? Therefore U is equal to R. It's very easy fast. You just have to take U to be equal to 1. RU should be in U. If you take U to be equal to 1, the entire R belongs to U. That means U is equal to R. Now 7th exercise. If R is a ring and this, let us take some element in R, and let us form a set T, and this consists of set of all x in R such that Ax is equal to 0. Prove that T is a right ideal. Prove that T is a right ideal. So what we are doing is that we are taking an element A in R, that R is in a ring, and you are forming a set T, and T consists of all those elements in R such that A into x is equal to 0, and this is a right ideal, right ideal, and I can easily verify this also. So first of all, we see that T is non-empty. This is non-empty because proof T is non-empty because why? Because if I take A to be equal to 0, then 0 into x is equal to 0 means the entire x will, this set T is non-empty, because if I take 0 belongs to R, then what about A into 0? A into 0 is again 0. So sorry, 0 is again 0. Therefore, this set is non-empty because this set has 0 in it. So T is non-empty because this happens. Now we need to put the right ideal. So for right ideal, so first we need to put the subgroup, and then we need to show, and then we need to check whether it is, first we will show that T is a subgroup with respect to addition, right? T is subgroup. So for that it is enough to show that if we take two elements in T, we just verify A minus B belongs to T. So we just take A to be equal to, here we have two elements, let us take two elements, let us take AB in T. That means Ax is equal to 0 and Bx is also equal to 0. Now what about A minus B? So A minus B is nothing but Ax minus Bx. Ax minus Bx. So this is nothing but A minus B into x. A minus B into x. Actually, we need to show that this also belongs to 0. So we will show. So if we take two elements in T, then these two will happen. Now what about, let us take this Ax1, Bx2. Ax1, B, okay, let us take two elements to be x1, x2, right? So we will do easily. Let us take two elements x1 and x2 in T, because A is fixed. We should not change A. So we need to prove x1 minus x2 is also in T. So x1 belongs to T, x2 belongs to T. That means Ax2 is equal to 0 because A is fixed, right? Ax2 is equal to 0 and Ax1 is equal to 0 and Ax2 is equal to 0, right? Now what about x1 minus x2? So what about Ax1 minus Ax2? Ax1 minus Ax2, or what about A into x1 minus x2? This is nothing but Ax1 minus Ax2. This is 0 minus 0, this is 0. This implies A into x1 minus x2 is equal to 0. This means x1 minus x2 belongs to T, right? So we are taking two elements in T. We have proved x1 minus x2 belongs to T because T consists of all those elements such that x is equal to 0. So all those x is equal to 0. So here x is x1 minus x2. So therefore x1 minus x2 belongs to T. Therefore it is a subgroup. Now for second condition is right ideal, means we need to prove SR, right? So SR belongs to SR belongs to T, right? So we will prove ST belongs to, we will prove TR, we will prove TR belongs to T. Yeah, this is a condition for right ideal. So for right ideal we need to prove SR belongs to S. So here instead of S, I am going to write this as T. So let us take TR belongs to S. Let us take T to be equal to some element in A, some element whose Ax is equal to 0. Let us take R to be an element from a ring, and clearly that we will have this to be an ideal. Now let x belongs to R, right? Y belongs to T. So what we need to prove? xy, right? Left ideal means RS, right ideal means SR. So what we need to prove is We need to prove yx belongs to t, right? This is a condition for right ideal. If I am taking x to be in R, y to be in S, we need to prove yx belongs to t. Now t is a right ideal, as you know that x equal to t. Okay, so we need to prove this yx belongs to t. That means we need to prove a into yx equal to 0. This is the one we need to prove, right? So this is the one we need to prove, a into yx equal to 0. Now so we will prove this. So we have y belongs to t, so this implies ay is equal to 0 because y is in t. So if element is in t, then a by ax is equal to 0. Therefore ay is equal to 0, right? Now what about axy, sorry ayx? So I can write ay into x, and ay is 0, this is 0. Therefore yx belongs to t. So therefore this is the set x such that ax equal to 0 is a right ideal. Actually you can prove any problem in your own if you understand the definition of the ideals, right? That is left ideal, right ideal, subgroup, subring, etc. Now we will prove 8th problem. The 8th problem is now you just take the exercise. So now we have proved, just now we have proved set of all x such that ax equal to 0 is right ideal, right? Is a right ideal of R. Now just take exercise. Let us name some other set. If u, this is 9th exercise. So if u is left ideal, if u is left ideal of a ring R, then lambda of mu, that is set of all elements in R such that xu is equal to 0 is a prove that is a two-sided ideal of R, is a two-sided ideal of R. So we need to prove that this set is left ideal as well as this right ideal. Here we are having u to be a left ideal, and we are forming another set lambda of u, that is set of all x in R such that x is equal to 0. So we need to prove that this set is a two-sided ideal. That means we need to check that it is left ideal as well as right ideal. So very easy process. So for left ideal, so first we will verify that it is a subgroup, right? So it will be easy subgroup, and the same process that we did for the previous problem. You just take two element in lambda of u. You just take two element in lambda of u. You just verify x1 minus x2 belongs to lambda of u. So I'll give you hint. So you just take two element in lambda of u. That means these two elements belongs to lambda of u. That means x1 u is equal to 0, x2 u is equal to 0. Now what about x1 minus x2 into u? I write this as x1 u minus x2 u. This is equal to 0. That means x1 minus x2 belongs to lambda of u. Therefore it is a subgroup. Now we need to put the left ideal. So our left ideal, let us take this to be equal to S. Our R is the ring, R is the any ring, R is any ring. So we need to prove for every R in R, every S in S, for every R in R, every S in S, RS should be in S, and for right ideal, for every R in R, S in S, SR should be in S. Actually you can easily verify. So just take R to be some element in ring R, and S to be equal to, let us take some element S in lambda of u, and you just verify that this belongs to S, right? It's a very easy exercise. So you can refer page number 312. Actually I have proved the entire thing. I have proved 80%. The only thing is you have to take two elements and you have to verify that the product is also in S, that is RS and S are also in S. And now we will prove that intersection of two left ideal is again left ideal. So we have to, you just go through the page number 312 for the solution for this problem. I think you can prove in your own. Now we will prove that the intersection of two ideal is again ideal. Intersection of, so far already we have proved intersection of two right ideal is again right ideal, intersection of two left ideal is again left ideal. Now we will prove 10th exercise, intersection of two ideal is again a ideal. So similar way, same process. So you just take two ideal. So two ideal means that is a subgroup as well as it is left ideal as well as right ideal. Now we need to prove that the intersection of two ideals again ideal. So let us take S1 and S2 be two ideal. So S1, I give you a overview of the proof. Let S1 S2 be ideal. So this is a subgroup as well as it is right ideal as well as it is left ideal. This is also a subgroup as well as it is right ideal as well as it is right ideal. Now we need to prove S1 intersection S2 is again an ideal, is an ideal. That means we need to prove that S1 intersection S2 is subgroup, and then we need to prove it is a left ideal as well as it is right ideal. So first we will prove that S1 intersection S2 is a subgroup. So clearly it is a subgroup because S1 is ideal, that means S1 is a subgroup, S2 is ideal, that means S2 is a subgroup, S1 intersection S2 is a subgroup because intersection of two subgroups again subgroup. Now for second condition, we need to verify RS belongs to S, RS belongs to S1 intersection S2. So that means you just take an element R in R, S in S1 intersection S2. Need to prove that RS belongs to S1 intersection S2. Now we can see that this R belongs to R, S belongs to S1 as well as S belongs to S2. So S belongs to S1, S1. This means S1 is a ideal. That means RS also belongs to S1, SR also belongs to S1 because it is ideal. It is left ideal as well as right ideal. And clearly S belongs to S2, and that means RS belongs to S2 as well as SR belongs to S2. Right? Now we need to prove that RS, we can see RS belongs to S1, RS belongs to S2, SR belongs to S1 as well as SR belongs to S2. So therefore RS and SR both are in S1 intersection S2. That means it is a left ideal as well as it is right ideal. It's a very easy proof. You can write proof in your own, right? So we have RS is in S1 as well as RS in S2 because S1 and S2 are ideal. So that means it is left ideal as well as right ideal. So if we combine these two, we will have RS belongs to S1 and intersection S2 and SR belongs to S1 intersection S2. Therefore it is left ideal as well as it is right ideal. So I think you can take exercise 11th, 12th as exercise. The same, actually we have 12 problems in this exercise. I have solved 10 problems. The only thing is I am leaving two problems for exercise. That is also 3 or 4 line problems. Now I give you one exercise problem for you. Let us take R to be set of all 3 cross 3 matrices A, B, C, D, E, F, G, H, I. The set of all 3 cross 3 matrices, and these all are okay. Let us take this matrix A, B, C, D, E, F. That is set of all 3 cross 3 upper triangular matrices. Let us take A1, A2, A3, 0, A4, A5, 0, 0, A6. That is, let R be the set of all 3 cross 3 upper triangular matrices, and these entries A1, A2, A3, A4, A5, A6 are real number. Let us take a subset to be, A00, 000, 000. Right? Now we need to show that it is left ideal, the same as I did in the exercise problem. First problem, it is left ideal, not right ideal, right? So S is the set of all nilpotent matrix, right? This will be a nilpotent matrix because when you multiply S square, it will be 0, right? So R is set of all upper triangular matrices and S is a subset of R. But if you recall and if intuitively you can see S as a nilpotent matrices. So it will be a left ideal, but it is not right ideal. Clearly it is not left ideal. If you take an element, you just take an element S and you take an element R, you just take an upper triangular matrices. You can take any entries. Let us take 1, 2, 3, 0, 4, 5, 0, 0, 6. let us take S to be 2 0 0 0 0 0 0 0 0, and you can see S RS will be in S, but SR will not be in S, right? So therefore this will be a left ideal, but it is not right ideal. Now there are some 5 more theorems I need to prove in ideal. The first theorem is a field has no proper ideals. That is, the only ideals of field are 0 and F itself. That theorem I need to prove. And if R is a commutative ring, then R is an ideal that we need to prove. And third is very important theorem, that is, a commutative ring with unity is a field if it has no proper ideals, that we need to prove. Prove that a commutative ring R with unity identity is itself a field if and only if it is no proper ideal. And then we need to prove let R be the ring with unity such that the only left ideals of R are 0 and R, show that R is a division ring. So we need to prove 5 theorems on ideal, and then we will move on to principal ideal, maximum ideal, and so on, right? So the next class I will we are not finished ideals yet. So the next class we will be solving 5 theorems. There are 2 important theorems in that 5 theorems. The very important theorem is a commutative ring with unity is a field. A commutative ring with unity is a field if it has no proper ideals. And second important theorem that we are going to prove tomorrow is prove that a commutative ring R with unity is a field if and only if it has no proper ideals, right? That the 2 important things that we are going to study tomorrow, and then we will be discussing principal ideal, right? Principal ideal. So you just go through today's class and you just take proper notes. Tomorrow we will be solving some more theorems on ideals, and then principal ideal and maximal ideal, right? So we'll see you tomorrow. Thank you.